This is AnalogFolk Academy. This is class number 1 of Artificial Intelligence, the Basics. It's a series of 6 classes to help you understand a little bit more what is artificial intelligence and what isn't. Even we'll start to see a little bit of the algorithms, how they work, and hopefully it will help you to understand how to use it more on a day-to-day basis and to make it part of the work that you do. So let's start by thinking of the basics of what makes today everything that we use on a daily basis in terms of technology. So I imagine most of us have heard the concept of ones and zeros, or even more so, the concepts of trying to think of ones and zeros as turning an on and off switch. So if you think about that, that is what makes computing today. So everything is either true or false. Everything is very specific and easy to describe. Artificial intelligence starts to embed a concept of being able to live on the uncertainty, of being able to move beyond the true and false. So covering a little bit of what I mentioned before, the on and off switch or the zeros and ones, is like taking a simple light bulb. You move the switch up, the light bulb goes on. You move the switch down, the light bulb goes off. But if you were able to combine 3 different switches on the same light bulb, then all of a sudden you can make it go on and off. Or you can even make it change color. So the first switch can make it go on and off. The second switch can make it change from blue to green. And the third switch can make it change from a green to something else like yellow. So that concept by itself, even though you have a combination of switches, it only allows you to do something very specific. What we started to call artificial intelligence is a layer on top of those zeros and ones that helps you move further and progress and be able to live in the uncertainty. So if you're still doubting what it is, so let's move forward to the next slide. I always use the concept of as clear as a blurry image. And what is the idea of that? If we put those 2 images in front of us that are blurry, and if we focus on the one that has the different set of lights, we can easily start to see that the yellow lights are the headlights of cars, and we can see that the red lights are the tail lights of cars. And if we even focus there, we can find a traffic light, and it's in green. And on the side, you can see a couple of yellow lights that look like the lights of a light post. So if we start to combine all of that together with what we've learned in the past and what we've seen, we can easily think that this is happening probably in the middle of a city, and we can start to notice a sidewalk on the left. So once we did that exercise, then if I were to ask the question of how many cars do you see on that shot, most of us can sit down and start to combine the different lights and our understanding of the size of the cars to count roughly between 8 to 10 cars. And this wouldn't take us more than a minute to do that. But what if we had to count the amount of cars on blurry images, and what if the amount of images that we receive is 1,000? What if we receive 100,000 images? What if we get 1,000,000 images? That's when we definitively need something that can understand images, digest them, and with a certain level of degree, it can let us know if something is a car, if it isn't a car. That's when this layer that we call artificial intelligence that can live in this uncertain world like we do is super useful. When I normally tend to call that smart automation. So what we're looking is for a way to do something that for us come naturally, but with computers. So this is an extra layer above those zeros and ones. Who is the star of artificial intelligence? Well, the star of artificial intelligence is really mathematics. It's being able to use a set of mathematical equations that can help us understand a little bit more a representation of the environment. It can help us start to play a little bit with abstraction. It can start to give us and be able to tailor information that we get from the surroundings and make sense out of it. And when I say we, what are we using? We're starting to use a computer. So on the image that you see there, in reality, if we were able to look at how artificial intelligence behaves, it looks more like the mathematical equations. But if we wanted to understand a little bit more from a higher level of what is happening inside of it, then you can see that image is very easy to see. So if within a shot, an image, then an algorithm were to see some triangles, it were able to understand some ovals, and it was able to make sense out of those shapes and be able to determine if those triangles, for example, are part of ears, and if it was able to determine that a part of that triangle is a part of a nose, and then those ovals, a couple of them, it was able to determine that those ovals were eyes, and one of those ovals is part of the nose, in this case, of an animal, then it might be able to say with a certain level of certainty that what is on that image is a dog. And to be honest, the idea of having that yes or no at the very end is because what can be in that image might end up being a cat. So at the end of that composition, of making some logic out of it, it could be right or wrong, the same way that us as humans, we can be right or wrong. If we were to see an animal that we had never seen before, we're going to use all of the information that we have compiled to come up with the name that we believe is for that animal. And if we were able to think about that when we were younger, when we're still learning and discerning what is a cat and what is a dog, we might easily say, oh, what is on that image, it's a dog, and it can end up being a cat, but then it helps us, it reinforces our idea of what a dog and a cat is, and we don't need to receive the specific rules of what those animals are. We start to abstract, we start to make sense out of them, and that's what starts to happen within these algorithms and within these mathematical equations that can help machines live in this uncertain world. If we started to look at this slide, what we compiled is a combination, a fake combination between the time that somebody spends on the phone and their age. So if you see there, we're saying that the younger the person is, the less time that person spends on the phone. And if we were to take those values in there and we were able to take a matrix and we started to place within a y-axis and then we started to place them on an x-axis, those values, then we can easily start to see that those values start to form and they have a correlation between them. So if we were to ask the question of how much time a person that is 20 years old can spend on the phone, then we can reach a conclusion, even though on the numbers that we have on that graph, 20 years doesn't appear. Why are we doing that? If we were able to draw something on top of those dots, which is going to happen naturally to us, then we can start to have a line. That line can help us make conclusions because we can start to correlate age with the right location of time. And once we start to do that, then we can use it in our advantage and we can use it to predict the future. So if we were asked the question of how much time somebody that is 40 years old is going to spend on the phone, we can come with a great idea and understanding of what that is going to be. So even though within this there is a linear equation, it looks very simple for us to be able to get machines to do that sort of predictions is very complex. And you cannot easily do that with the programming that we normally tend to have of the zeros and ones. And how does that happen? If we were able to abstract and get the equation of a linear function, that it's a very simple equation, and if you were able to look at the multipliers with having the a multiplying x, and then the final value that it's b, those values, the idea of those values, if you start to play with them, and if you were able to augment x, then you start to see how the line starts to grow up. If you were able to reduce x, you start to see how the line starts to go down. And if you start to play with b, you will be able to see how the line by itself starts to go up within the y-axis. And if you start to reduce b, you see how the line starts to go down. So what is the basic of artificial intelligence? Is allowing an algorithm to start to play with that a and b values, and it's able to start moving until you start to ask it, oh, how much time that somebody that is 20 years old will spend on the phone? How much time that somebody that is 5 years old spends on the phone? Until it starts to get the answer to all of those questions as close as possible to right. So once the machine starts to do that, so once it's able to play with the right A and B values, it starts to create an equation. So it starts to create an equation that you can ask questions to, the same way that when a person draws that line, we can start to use that as the basis to make some assumptions. But on the biggest sense, instead of just those A and B values, it looks something more like this very big mixer that you see on the picture. So the idea is there's tons of values that you start to play with to make sense out of the different things, because you're not only trying to correlate something as simple as the time spent on the phone and the age, you're trying to correlate what makes a cat, what makes a dog, and what makes like a camel. That is very different type of information that you're trying to compile, and you're using a machine to do that. So the amount of variables that the machine is going to be playing with is huge. So the amount of computational power that is needed is also quite massive. So how has this progressed? One of the things that has helped progress this discipline is the more machine power that you can have, that is happening with cloud computer, the more it started to progress, but also the more data you start to have. So the more that different databases of images are getting updated out there, so the more you can start to train that algorithm to get the right responses for the different sets of data and information. By getting the idea of databases and the images and starting to understand what makes each thing, what are the characteristics that make everything that we see and how we distinguish a chair from a sofa or a sofa from a table, that brings us back to what artificial intelligence is. So within our head is our logic. Purposely, part of what we have been doing through this class is trying to understand the characteristics of everything we see. It's helping us to think and make some sense out of a blurry image, and it's also helping us to understand more how we distinguish information, how we learn. So one of the basics of artificial intelligence is helping a machine do what we do in a very great way. So the first place to start, and the first place that it has started, is to understand our own logic. If we look at this image and we make sense of what makes a roller skate, and what makes a skateboard, and a scooter, you can easily start to see that even though they share a lot of similarities, you can focus on the differences. So you can easily see that the tires are aligned in a different way for the roller skate than they are on a skateboard, and even less so, the amount of tires from a skateboard are different to the amount of tires that you can see on a scooter. Still, you could easily start to think of the geometrical shapes that makes each of those elements. So you can start to see that there's a rectangle in the middle of a skateboard that it's accompanied by two semicircles at the side. You can even see that, yes, there's also a rectangle that goes in the scooter, but it doesn't have those semicircles. You can even look that the scooter has some steering, which makes you think that you can even think that there's like a rectangle that goes in the middle once you take a picture. So you can start to think of what are those things that make them similar, but at the same time, what are those things that make them different. So what we're doing at this moment is called abstraction. So we're trying to abstract ourselves a little bit further from the element, and we start to describe it. We started to make it easier to digest. We started to make it easier to understand. So initially, when artificial intelligence started and there was less computational power, what we're doing was done by very good mathematicians, where they will take the elements that the machine was trying to understand and predict, and they will start to do themselves this sort of abstraction. So they will be creating interesting mathematical equations or way of classifying objects. So before it even gets to the machine to make the idea of what are the characteristics that are coming from that element, there was a pre-filtering. There was a direct interaction with the human. Once the machine started to advance more and the algorithm themselves started to go further, and without going into detail, most of you probably have heard that one of the most mysterious and nicest artificial ways of intelligence is called convolutional neural networks, that will cover some of this class. Those are the ones that started to open the door to what we call machine learning, or some people start to call deep learning within machine learning, that it's a machine being able to figure out those algorithms. But let's still think that it is us and it is on us to make that classification. So focusing on the objects and understanding what they are made of is a great way of understanding what is happening inside of a machine. And even if we have a picture in front of us, there's never a 100% degree of certainty. We're looking at something and we're combining our overall understanding, but many times we might get surprised. And in this way, that is the idea of what we're doing with machines. They are not getting to 100% certainty, but they are getting to a close enough level of certainty to be able to play in this abstract world. On the examples that we have seen on the previous slides, where people were abstracting the characteristics before fitting it into the algorithm, on those examples, then when it's easily to break it, as soon as you get very big, bold, amazing images like the one that we see here that has a Spider-Man. If we look at the amount of pixels that make up the images, it will be very difficult for us to abstract what are those characteristics that make up and that appear within this image. And if we were to focus just on this image alone, even less so, it would be more complicated to do an algorithm by hand of thinking what are the equations that would describe each of the different characters, let's say, from the superhero magazines. So one way that we started to do that, as mentioned before, is using algorithms to be able to do that for us. So we're going to go through a very simple example of understanding the numbers that are written by hand from 0 to 9 and how an algorithm is able to understand handwriting. And that will help us to go deeper on how the algorithms that are used here work. So if we were to take a number 8 that was written by hand, and then we were to think and getting it into a matrix, and we were able to look at each of the spaces that somebody has drawn, and if we look at it and think that it's a 20 by 28 by 28 matrix, and that we start to get each of the pixels that make up the number 8, then all of a sudden we have the information that is good enough to start to feed it into an algorithm, to start to feed it into a machine. And of course, in difference to us, that we can look at all of the number 8 together, we'll be feeding all of those values one by one. So we will be feeding the first value within the matrix, that is a value 0.0, and then we'll be feeding the second value, that is a value 0.1, 0.2, until we feed in every single of those values into a machine. And what the machine is going to start to do is going to start to look for the correlation between all of those values within that matrix and start to understand the different shapes that it gets from the number 8. And by looking at the combination of those different shapes and how those different shapes align, at the end of the day, it's going to be able to say with a certain level of certainty that is the number 8 versus the number 9 or the number 7 or the number 4. And the more cumbersome we draw the number 8, the more we can make the machine doubt itself. So the rounder we draw the number 8 and the better we draw the number 8, the higher will be the level of certainty that it's a number 8. But the more we make the number 8 resemble a different number, so that value is going to go down. And also part of this process is feeding these values to help the machine determine what are the characteristics that make up each of the numbers. So the more values we feed in and the more variety of values, the better we are going to get this algorithm to work. And how do we train the algorithm? That is one of the biggest questions. The way that we train the algorithm is by saying if it's right or wrong. So we feed in a number 8. We know that we're feeding in a number 8, and if at the end it tells us it's a number 9, we tell the algorithm no, and then it goes back adjusting all of the values, and then we feed in again the number 8 until it tells us yes, it's a number 8. So we say to the algorithm it's right. So we reinforce the algorithm that it was able to adjust itself to determine if it was a number 8. And then we can take images of hand-drawn number 8 that were not used to train the algorithm to make it determine if it's properly trained to look at all of the characteristics and varieties of that number. To help you understand how accurately it can do this, even in the 1990s, these algorithms were already used by banks to be able to understand handwriting in checks. So that means that if they are well trained and with the proper mathematical equations, they can go a far way. And when they are very well tackled and when we find the right problem to use it, they work quite well. Again, going back to that concept, purposely on this class, I didn't start talking about why it's called artificial intelligence and where does it come from. So one of the things that we've been doing since very early stages was understanding how we learn and how we are able to progress our learning. While doing that, there was a model of thinking that we were emulating what was happening in the brain with what we call an artificial perceptron. That is the idea of the sense of artificial intelligence. And how we did that, we got inspired by the brain, since the brain works as a single organism, even if it's made up of different parts, and then it's able to combine the information that it gets and it's proper output. We purposely didn't start by going into the biology side of intelligence, because even though artificial intelligence was inspired by our understanding of the brain, by our abstraction of how the brain works, on being able to have something as powerful as a neuron combine a set of information to provide an output, to create then the sense of this artificial perceptron that it's used throughout many parts of artificial intelligence, mostly neural networks. There is not a direct correlation on how we learn in the biology with the sense of these mathematical equations. So that's one of the reasons I don't start by there, even if it's part of the history of where it started. So what is the sense of the perceptron, moving away from the biological side of the equation? The sense of the perceptron is to have a bunch of input, is to have a different amount of inputs that go into a centralized location, and then an output is provided. So to the example that we have shown before, a perceptron will receive that information of the ears, it will receive that information of the ovals, it will receive that information of the triangles, it will receive that information of the fur, and it's going to be able to combine it via a mathematical equation. It's going to come out with an output. Like mentioned before, it can come out with an output saying it's a cat, or it's a dog, or it's any sort of animal. Or like we saw in the previous example, and the one that we can see in this image, it can come with a conclusion that what it's getting, it's a number 8. And how it does that, it brings us to the concepts that are used throughout a neural network, such as weights. The concept of weight is very important. Think of weights of like the mechanism of how much power do you give to a vote. So when we are determining if a dog is a dog, what is more important, the ears or the nose? What is more important, the shape of the triangle in the nose? To be honest, when the algorithm starts to get trained, it doesn't know what is the most important thing. But the more we feed information, the more we feed images of animals, or the more we feed images of numbers, and we start to tell it it's right or wrong, and the more it starts to adjust its weights, then the more it starts to know what are the most important characteristics that make up the object. So what are the characteristics that carry the highest weight? As mentioned before, the idea of machine learning is letting a machine do all of that abstraction by itself. So one very interesting thing that happens is when you use this sense of machine learning, at the very end, in difference to when we had seen the example of the roller skates, of the mathematicians having to come up with the characteristics that make up what a roller skate is or what a skateboard is, actually those characteristics are found by the machine itself at the very end. Once it starts to feed in all of this information and how to adjust the weights, and when it's able to use the algorithms that are inside of it, then it's able to abstract the very rich information that makes up what are the characteristics to define a cat, what are the characteristics to define a dog. And one of the interesting things that is allowing us to do at this moment is to do some experiments like the one that we see in here. So an experiment was done when a set of manga characters were fed into a convolutional neural network, and the convolutional neural network was able to abstract all of the characteristics that made up the manga characters. Once it was able to abstract those characteristics, then we could feed in different type of information, different type of randomized information, and the algorithm itself is going to start to give us manga characters. So all of those manga characters that you see there are randomly created by a trained algorithm. What is also artificial intelligence allowing? One of the things that artificial intelligence is helping is with the human plus computer interaction. So it allows a machine to be able to communicate different, to interpret different. So it allows machines to be able to understand images, to make sense out of images. So for example, if we look at Facebook, instead of thinking that Facebook is just a social network for likes and for sharing information, actually at the heart of Facebook, the most important piece of it is artificial intelligence. It's looking at the images, it's looking at the interaction that each of the individual has with the images, it's looking at the text, is making sense out of the sentiment out of it, and what then each individual ends up getting. It's a completely different tailor-made storyboard from Facebook that is showing the information that the algorithm think it's relevant to that person. That also brings us to a very important individual within the history of artificial intelligence, that is actually Jean LeCun. And a lot of his breakthroughs were within banks and finance institutions. When I mentioned the example of being able to read checks, it was a lot of his research that made that happen. But around 2012, he was able to advance even more a network that is the convolutional neural networks to be able to understand images in a machine of artificial intelligence with a nice layer of images and shares, and is run by Jean LeCun. And that is also one of the complexities, since these mathematical equations become more and more complex, and it's using a combination of those algorithms that is one of the complications of why it is so difficult to determine why something happened inside of that algorithm. Even if you can trace the logic, you cannot be 100% certain of what happened. And that is also one of the difficulties that is arriving to artificial intelligence. Another great progress happened in the field of natural language processing. So for many years, we have been making sense of the way we talk, the words we choose. We have been able to analyze the different type of languages and the correlation of those words, the sounds, but we were far away from being able to allow a machine to be able to interact with us directly and be able to understand our ways of communication. And even more so, that within communication, if it's written, it starts to be a little bit more straightforward. But if we have verbal communication, also the tone of voice gets in the middle of communication. But if we look at natural language processing from a very high simplistic level, we can start to see that we are making sense, and we have always been making sense out of the syntax. We have been making sense out of each of the words and how those words are written and how they correlate. But one of the things that is happening at this moment, it's being able to decipher each of the words that come into a machine, how they interconnect, to then be able to look into something that will be a database to provide the most accurate response. The interesting thing is, if you think of natural language processing, and if you think of natural language processing communication with a human to a machine, a human gives the communication in a very human way, then it passes through sets of algorithms that then decomposes it and starts to convert it into something that the machine cannot understand, all the way down to zeros and ones. But then the machine gets an appropriate response. It starts to compile that information, and it tries to provide a response in a very human way. So something like this is happening all the time when we're using things like Siri, when we're using things like Cortana, when we're using anything like Alexa. So, and one of the final concepts that I wanted to be very clear is the sense of some people saying, okay, the machines are creating art, but this brings us to even more so the idea that machines are dreaming. To be honest, it's still not really that a machine is dreaming or a machine is creating art. What is happening is that some of these algorithms, if you properly train them with the right set of data, then you can start to make them be able to create, like the example that we saw of the different manga characters. If you were able to train one of these algorithms to understand the characteristics and to abstract that of a manga character, if you were able to train one of these algorithms with a specific type of photography that is of your interest, then with randomizing the values, you can make and the algorithm start to create and feel the sense that by itself is generating art. It's not necessarily generating art, actually it's generating biased information because it's based on the information and the values that you were able to train it with. So what is the output that it's going to be creating? It's only black and white pictures. It's not going to progress further. But if you were to train it with pictures with different colors, the output that it's going to be creating is a combination of colors. So it brings us back to the importance of the data that you train the algorithm with. So one thing that also makes people nervous when using these great mathematical equations is that the more you start to use these trained algorithms in the wrong location, the more bias it's going to be. So a great example is if you were to take one of these algorithms and train it to be able to know if somebody should be getting a mortgage or if they shouldn't be getting a mortgage, if you were to train it with data, let's say from the United Kingdom, the idea is that algorithms shouldn't be trained and used in the exact same way that is used in the United Kingdom in a completely different region because the parameters, the information and the abstraction that it should be getting is completely different. So I hope this helped to clear some of the doubts of what artificial intelligence is and what it isn't. I'll see you in class number 2 that it should be released soon. Hopefully you can continue joining us through the set of 6 different classes that will help us completely dive, understand, and fully answer that question, what are the next things and that we should be doing with artificial intelligence.